mixture of two salt solutions. Now, if they are able to form to any other product compound, I need to give sufficient time for them to interact with each other, or to have interactions with both salt solutions or both cations. I need to give sufficient time, right? So that's why I will do slow process. Now, whatever the product obtained, I call it as addition product. These addition compounds are classified into two types. They are classified into two types. Double salts, we call them as double salts, or we call them as complex compounds or coordination compounds. Complex compounds or coordination compounds. How to differentiate them? But both are obtained from addition of two salt solutions. So both are obtained from same mixture of same salt solutions. So how to differentiate them? If these double salts, if I dissolve them in water again or in particular solvent again, they furnish ions similar to individual salt solutions. Right here, I am mixing two or more salt solutions. Huh? What are the ions present in it? What are the properties do those individual salts possess? All such properties are retained here. If all such properties are retained, then we call them as double salts. If not, complex compounds, right? So these double salts should furnish ions similar to individual salt solutions. Similar to individual salt solutions. Example: ACl aqueous mixed with MgCl2 aqueous. This on crystallization. This on crystallization gives KCl dot MgCl2 dot 6H2 crystals. We call this as, this ore is called, or this mineral is called carnallite. Right? Similarly, by mixing ferrous sulfate, ammonium sulfate, you will get Morse salt. Morse salt. Morse salt is FeSO4 dot NH4 twice SO4 dot 6H2O. Means what are the ions it should furnish? It should furnish. It should furnish Fe plus 2 ions, NH4 plus ions, SO4 2 minus ions also. Right? If it furnish ions similar to individual salt solutions, then only I call it as double salt. Otherwise, I call it as complex compound. Now, note, if you have any double salt furnishing one metal in +1 state, another metal in +3 state, such double salts are called as aloes. So double salt having one metal in +1 state, another metal in +3 state is called as, we call it as alum. We call it as alum. Example. Potash alum. Potash alum. What is it?
K2SO4 Al2SO4.
K2SO4 dot Al2SO4 thrice dot 24H2. If any double salt, if it is able to furnish M+2 ions and M+3 ions, then it is called pseudoalum. Right? So I am not giving any much examples for it. Instead of potassium, I will take magnesium, nothing there. Right? Now coming to coordination compounds or complex compounds. What they should do? They should not furnish ions similar to individual salt solutions. We call them as complex compounds or coordination compounds. Example. I am taking copper sulfate, CuSO4 aqueous, mixed with ammonium hydroxide aqueous. Initially, what happened? Initially, CuOH twice will precipitate, right? That will be soluble again to form CuNH3 4 times SO4 complex dot 4H2O. This is the complex obtained. Now, this will furnish, what are the ions furnished from here? It will furnish CuNH3 4 times +2 ions and SO4 2 minus ions, but it is not able to furnish copper +2 ions and it is not able to furnish NH4 plus ions, right? So as this is unable to furnish ions like individual salt solutions, then it is called complex compound or double salt. Clear? Respond. Any questions in it? No. I am taking one more example. Six moles of KCN with FeSO4 gives rise to K4 FeCN6 plus K2SO4. So what are the ions furnished by this? It will furnish K plus ions, FeCN6, 4 minus ions, but is not able to give Fe+2 ions, right? So that's why we call this as complex compound. So what you observe the difference between double salts and complex ions. Double salts are given by, connected by a dot. Complex ions are something we are mentioning in square brackets. Whichever I mention in square brackets, we call it as a coordination sphere, right? Whichever I am writing in square brackets, we call it as coordination sphere. Of course, Werner gave some explanation that we will discuss later, right? Now we will see the terminology we use in complex compounds. Terminology. For example, I am taking one complex K4, FeCN6. This is the complex I am taking. In this, we call this part as, whichever mentioned in square brackets, we call this part as coordination sphere. or we call it as coordination entity. Coordination sphere or coordination entity. Whereas whichever present outside square brackets, we call it as counter ion. We call it as counter ion. Then this is called central metal atom or ion. Central metal atom or ion. Central metal atom is connected to species called as ligands. These are connected to ligands. In that, this number, whichever is mentioned, that number is called coordination number. Ligands are nothing but lone pair electron donors, or we call them as Lewis bases. Correct? Huh? Central metal atoms are lone pair electron acceptors, or they behave as Lewis acids. Coordination number means number of lone pair electrons donated by ligands or accepted by central metal atom. Lone pair electrons donated by ligands or accepted by central metal. We call this as coordination number. Any questions in this? Right. This counter ion always try to balance the charge over coordination sphere. This counter ion always balance the charge, or can I call nullifies the charge? Nullify the charge of coordination sphere. Do you have any questions up to here? Online, right?
No, sir.
Here, one more statement. Generally, ionizable groups are present as counter ion. If I take one example, Cu NH3 4 times SO4, blue color complex. What is counter ion here? This is the counter ion. Now I am taking K3 FeCN6. Now which is counter ion? Okay. None. Next, sir. Complex polyhedron. Now, once open your target booklet. complex polyhedron. Correct? Next slide reading. The same thing we are discussing now. There also they have given that list of what is counter ion, what is coordination sphere, what is ligand. Just let me open this. See this? We are discussing introduction in which addition compounds, Morse salt is done, right? Then K4FeCN6, coordination entity, we are discussing this, right? Oh, sorry, over, coordination entity over, central atom or ion, ligands, coordination number. Now what they are saying, coordination number of central atom is determined only by number of sigma bonds formed by ligands with central metal atom or ion, or pi bonds, if formed, are not counted for this purpose. Means what they are saying, only we need to count sigma bonds or coordinate covalent bonds. We should not count. Then ionizable groups are written outside the square brackets in outer sphere and are called counter ions. Same example, right? The pi bond is pi electron cloud donor, no? It is not species. For example, if it is a benzene, every carbon is giving electron cloud. Every benzene have partial charge. So because of partial charge, it behaves like ionic interaction, no? So we cannot show that this bond is having 2 electrons, or we cannot show particular direction of it. So that's why we are not able to count it, right? So what I have to write, just a moment. What I have to write, under coordination sphere, number of lone pair electrons donated, or I will write sigma bonds, correct? Or I will write coordinate covalent bonds. Response, sir. Right? Now I am taking the next heading. What is it? Coordination polyhedron. Coordination polyhedron. Yes, sir. Coordination polyhedron. Listen, sir. Based upon number of ligands, because all ligands are forming sigma bond. Why we are counting sigma bonds only, or why we are counting coordinate covalent bonds only? Coordinate covalent bonds are directional, right? Sigma bonds are directional. Then they will decide geometry of the molecule, right? So this is the reason why we are counting only them, right? What is coordination polyhedron means? Based upon number of coordinate covalent bonds, or based upon number of ligands, we will decide geometry. If there are only 4 ligands surrounding it, square planar, or maybe tetrahedral. 5, trigonal bipyramidal or square pyramidal. 6, octahedral, as such, right? So when ligands surround central atom, ligands surround central atom, they are oriented in certain direction, to impart some geometry. That geometry is called coordination polyhedron. If a coordination number is 4, now what is coordination number? Already we have seen. Number of ligands or number of sigma bonds is called coordination number. If a coordination number is equal to 4, we can have two geometries possible. What is it? Maybe a tetrahedron or square planar. So I write central metal atom. These are ligands, 4 ligands. Or this is central metal atom. These are the 4 ligands. If a coordination number is 6, then octahedron. Already you know the properties of octahedron. What is it? Axial and diagonal. Response, sir. Axial bond length and diagonal bond length must be same. Correct? This is the diagonal. This one is diagonal. This length and this length must be same. Then it is called regular octahedron. Next, coordination number 5. If a coordination number is 5, remaining all coordination number. Generally, coordination number 4 and 6 are general. Most of the complex compounds will have coordination number either 4 or 6. Coordination number 5, 3, 7, 8 are very rare. Right? That's why we are discussing that coordination number 5 separately. So, coordination number 5, 3, 7, 8 are rare. Will you understand now? So if I am taking coordination number 5, geometry possible. Trigonal, bipyramidal, and one more is also there, na? Square pyramidal. In case of trigonal pyramidal, bipyramidal, we studied one rule, if you remember. Axial bond length is greater than stop talking. Double bonds, lone pair electrons, right? Multiple bonded atoms and lone pair electrons. More electronegative elements prefer axial position. We call this rule as Venn rule. So we are done with complex polyhedron. What is the next idea? Huh? Oxidation number of central atom. Oxidation number of the central atom means how many electrons gained or lost by the central atom. Generally, we write that in square brackets by adjacent of that respective element, right? Oxidation number or state of central atom. All right, write oxidation number of central atom. After removing all the ligands, after removing all the ligands, charge present over central atom. Correct, sir? Example. I am taking nickel tetracarbonate, NiCO4. Now tell me what is the oxidation number of nickel here? 0. K3 FeCN6. What is the oxidation number of iron? +3.
3.
K4 FeCN6. Now
Plus
plus
2.
2, plus 2, etc. These are all oxidation numbers. What is the next heading? Homoleptic and heteroleptic. Homonuclear complexes. Homonuclear complexes. Heteronuclear complexes. Homoleptic complexes. Heteroleptic complexes. Homonuclear complexes, heteronuclear complexes, homoleptic complexes, heteroleptic complexes. Homonuclear complexes means only one central atom. Here, two or more central atoms. Here, only one type of ligand. Here, two or more types of ligands. Example. Same, I am taking K4 FeCN6. How many central atoms are there? 1. In this case, how many central atoms? 2. We call these ligands as bridged ligands. Cobalt. Right? Of course, both may be same also. Both you can take cobalt. Then also 2 nuclear, right? Heteronuclear ligands, right? 2 metal atoms having ligands connected in different ways, right? That's all. Then they are heteronuclear. Now, homolepticity means only one type of ligand. So NiCO4 here, correct? Only one type of ligand. Here I am taking platinum, fluorine, chlorine, bromine, iodine, 1, 2, 3, 4. Then OH, NH2. Now see how many ligands are there. One, two, three, four, five, six. 6 charge must be balanced. So I am taking this. Right? Here, what is the oxidation number of platinum? +4. Nickel, 0. Cobalt, hey, iron is complex, man. That's why it is called homonuclear, nucleus, which is present at the center. Right? Iron is the center, central atom. So that's why homonuclear. Now here, what is the oxidation state of iron? Iron is +2, okay. Cobalt. Cobalt and copper oxidation states I want. Copper is +4 doesn't exist. Copper +4 doesn't exist. Means here I have done one small mistake. That mistake is I have to take cobalt here, copper here. Now it is perfect. Here it is in either +1 state or +2 state. Both are possible. If I take +1 here, what about cobalt? Here 4 chlorines, 4 minus. 1 minus, here 1 minus. Total is 6 minus. Ammonia 0. So 6 minus charge should be distributed among 2. So I can take copper +2, cobalt +4. If I write copper here, what happens? Copper +4 I have to write. No, not possible. No, copper +4 state. Clear? Understood or not? Or you can write platinum also. Write platinum +4. Perfectly possible. Cobalt +3 is more stable, +4 is unstable. No? So if you take platinum, perfectly possible. Nickel also you can write. Clear? Next side reading, sir. Next side reading. Hard and soft acid base theory. Just a moment. Oh, here we have not discussed the strong, weak acids. The acid-base theory where we discussed chemical bond. Oh, sorry, chemical equilibrium. I think. I will upload. They changed the channels, so they might not delete it. See, sir. In chemical equilibrium chapter, we discussed acid-base theory. There we discussed in detail about all types of acids and bases. Arrhenius acid-base theory, Bronsted-Lowry acid-base theory, conjugate acid-base theory, leveling effect of water, acid-base strength series, Lewis acid-base theory. There we discussed Pearson's strong, hard, and soft acid-base concept. HSAB means hard and soft acid-base concept. Pearson, hard and soft acid-base concept. What are hard acids? Which have small size, high energy LUMO. LUMO means least unoccupied molecular orbitals. And molecular orbitals in that MO theory, which are empty. If the empty molecular orbitals are having higher energy, then it is under hard acid. Weak polarizability. So if they are not able to distort electron cloud, then they are hard acids. High positive charge, then they are called as hard acid. Examples: Mg+2, H+, etc. Hard bases, small size, observe, small size, high energy LUMO, high energy HOMO. Weak polarizability. High positive charge, high electronegativity. This is hard acid, that is hard base. Example, F-, carbonate, etc. Soft acids, larger size, soft base, large size. Low energy LUMO, high energy HOMO here, low energy HOMO. Weak polarizability, high polarizability. Here also, weak, high. High positive charge, low positive charge. High electronegativity, intermediate electronegativity. Is it clear? Hard acid, hard base, soft base. Now, so that introduction in 1963, R.G. Pearson extended and generalized the qualitative correlation between Lewis acids and Lewis bases by classifying them into two categories, hard and soft. This qualitative concept explains the stability of metal complexes. Right? This theory explains the stability of metal complexes and the mechanism of their reactions. This concept is also known as hard and soft acids and bases theory. Now, classification of Lewis acids into hard, soft. Hard, soft. Right? H+, 1A group. Hydrogen, lithium, sodium, potassium. 2A group, beryllium, magnesium, calcium, strontium. This is Sn+2, tin. Aluminum +3, cerium +3, gallium +3, lanthanum +3, indium +3, chromium +3, cobalt +3, iron +3, arsenic +3, iridium +3, and so on. All these are list of hard acids, soft acids, hard bases, soft bases. All right. Now, in that borderline bases, they all are lone pair electron donors, right? Whether they are strong donors or weak donors, right? If they are weak donors, if they are not able to donate lone pair of electrons readily, then what about interaction? If central metal is there, one ligand is there, between metal and ligand interaction is strong. Means interaction is strong means polarizability must be high and it should be good donor. Correct? Good donor means electronegativity should be low. Or if it is strong electronegativity, it will not donate electrons. No? Means, can I say soft acids prefer soft bases. Same way, hard acids will prefer hard bases. Right? Is it clear? So, which ligands prefer central metal atoms means hard base ligands prefer hard metal ions, hard acid metal ions. Soft base ligands prefer soft acid central metals. Is it clear? Any questions on it? This is about HSAB. Now, once open your target, what they have given in it. Same thing, huh? They also gave the same list. Correct? Soft acids, hard acids. Ligands are also classified as soft bases, hard bases. What they said? Soft metals prefer soft base. Hard metals prefer hard base. Simple. Clear? So I am writing here. It has a note. According to Pearson, hard and soft acid base theory, soft metals prefer soft metal means soft acid. Lewis acid man, lone pair electron acceptor. Metals are lone pair electron acceptors. Na? That's why I wrote soft metal. Means soft acids. Prefer soft base. Hard acid prefer hard base. Now here I am writing hard acid. What are hard acids? Hard acids. Just now we have seen 4 conditions we have seen na hard acids. Then high energy LUMO. Better I will do. Hard acids. Small size. High energy LUMO. And then weak polarizability. High positive charge. Example. They have given in your list. In your target booklet, they give example, no? H plus, Li plus, Na plus, K plus, Be plus 2, Mg plus 2, calcium plus 2, strontium plus 2, lanthanum plus 3. Any other? Cerium plus 3, plus 4. Titanium plus 4. Manganese plus 7. Iron plus 3. Cobalt plus 3, etc. Next. Soft acids. What are soft acids? Large size. Here. Low energy, LUMO. Highly occupied molecular orbital. Right? Molecular orbital occupied but having high energy. LUMO means unoccupied molecular orbital having lower energy. So low energy, LUMO only. Polarization. High polarizability. low positive charge. Right. Examples of soft acids, sir. Examples of soft acids. Lower oxidation state now copper plus there, Ag plus, gold Au plus, thallium plus 1, and thallium plus 3 is hard, plus 1 is soft. Hg plus 2 is hard, Hgu2 plus 2 is soft. Correct, sir? Cesium plus larger size. Correct? That's why soft. Palladium plus 2. Next. Platinum plus 2. Platinum plus 4. Calcium. Hey. Calcium plus 2 we wrote here, ma'am. Maybe cadmium plus 2. What, man? It is hard acid. Cadmium plus 2. D block. Cadmium plus 2. Then any other given? That's all, etc. Now, hard bases. Conditions for hard bases. Small size anion. Small size anion. High energy HOMO. It is not working. High energy HOMO. Polarizability. Weak polarizability. Both hard bases, hard acids, both have weak polarizability. High electronegativity. Example. Electronegativity high, fluorine. Response, sir. So F minus, OH minus, Cl minus, CO3 2 minus, water, more electronegative atom oxygen. Then ammonia, nitrogen also more electronegative. Means all amines RNH2, hydrogen N2H4. Then CH3COO minus acetate ion, phosphate PO4 3 minus, SO4 2 minus, alcohols, alkoxides, ethers, etc. Soft bases, exactly reverse. Large size, low energy HOMO, high polarizability. Correct. Intermediate electronegativity. Hydrazine, NH2 bond NH2, hydrazine. Example. Either CH3 twice O, diethyl either C2H5 twice O, diethyl either. Now, if it is oxygen, more electronegative. If it is sulfur, RSH. If it is ROH, more electronegative. Therefore, hard. Instead of oxygen, if I take sulfur, soft. So RSH, RS minus, R2S. Now larger anions, I minus, correct? CH3 minus, H minus. H minus is larger than F minus, correct? In periodic classification, we have seen. Then Cn minus, cyanide, isocyanide, carbonyls, alkenes, benzene, any other given? Given carbon monoxide, etc. Done. So this is about hard and soft acid base theories, right? Now, borderline. In acids, borderline is there. In bases, also borderline is there. Those who are able to bond via hydrogen bonding. Hydrogen bonding molecules. They're all borderline. Right? They prefer to form complexes with Fe plus 2, cobalt plus 2, nickel plus 2, copper plus 2, zinc plus 2, lead plus 2, boranes, sulfur dioxide, nitrosyl, etc. Right? These are all borderline acids. Same way, borderline bases. C6H5 NH2 aniline, C5H5N hydrazine, Br minus. I minus is, see this, I minus is soft base, Br minus is borderline. Nitrite ions NO2 minus, sulfite ion SO3 2 minus, nitrogen, etc. These are all borderline bases. Right? This is about HSAB, hard and soft acid base theory concept. Next, sir. Next ID. Based upon charge of first one. Right. So next ID, classification of ligands. This HSAB no need to study, sir. It is mentioned in our target booklet. That's why we are seeing. No need to bother. Right. Just remember the conditions. Right. If it is high electronegative elements prefer to interact with if metal and ligand interactions are strong, means they are stable complexes. Metal ligand interactions are strong, then they are stable complexes. Stable complexes means they are strong, means what should be ligand? Ligand must be a good donor, means its electronegativity must be low. Electronegativity must be low. Metal should accept lone pair of electrons. So metal atom should have more empty orbitals, or its charge must be high charge. Respond. So higher charge central metal atoms, good lone pair electron donors prefer to form strong complexes or stable complexes. Such metal atoms are called as hard acids. Such ligands are called as hard bases. Hard acids prefer to form strong covalent bonds with hard bases. Soft metal atoms prefer to form stable complexes with soft bases. That's what we are saying. Soft prefer soft, hard prefer hard. So this gives one basic idea about stability of complexes. Clear? Respond. Now observe where iron is. Iron, Fe plus 2, Fe plus 3. See, where iron? Fe plus 3. Fe plus 3, higher charge means hard. Plus 2 is borderline, right? So it is comes under not soft, no? They are not soft. So they are moderate or hard. Now, hard prefers hard means iron should not form complexes with iodine. FeI3 doesn't exist. We discussed at that point in D and F block. Correct or not? Right? Iron can form complexes with chlorine. FeCl3 possible. FeCl2 possible. F2 possible, but not FeI3. Clear? Understood or not? So to form stable complexes, hard will prefer hard. That's all. Don't think much. Response, sir. Online. Any queries?
No, sir.
Now coming to classification of ligands based upon charge. Positively charged ligands. This is ligands. First one. It will form complexes with cyanides. See, but cyanide, observe this. Where is Cn? Soft. But iron is in hard. Therefore, that complexes are ionizable. Or we call them as labile. What we call them as? Labile complexes. So K4FeCN6 is labile complex. So it can ionize into ions on strong withstanding, on long withstanding. Clear? Are you able to understand? Now see cobalt. Cobalt. Where is cobalt? Cobalt, hard. There is it. Cobalt, hard na? Now, cobalt forming complexes with ammonia. Where is ammonia? Hard. So cobalt complexes with ammonia are stable, not ionizable. Very strong, right? Copper. See copper. Where is copper? Copper. Where is copper plus 2, man? This is copper plus 1. So copper plus 2 definitely comes here. I have not written, right? Copper plus 2 complexes with ammonia are stable. Are you able to understand? In that way, we can write. Right? It gives one idea. That's all. Right. Now coming to next. Classification of ligands based upon charge of ligand. First, regarding positively charged ligands. Yes, Mithil Bharat. Right. Now see this, sir. We are discussing types of ligands, positively charged ligands. Name of these ligands end with EM. name of these ligands end with EM. For example, NO plus. If it is NO, nitroside. NO is called nitroside. What about NO plus? Nitrosalium. Right? NaH2, NaH2, hydrazine. Then NaH2, NaH3. Hydrazinium. Etc. Right? Name should end with IUM. I am completing nomenclature of ligands also here. Second one, neutrally charged ligands. Neutrally charged ligands. Example, carbon monoxide, nitric oxide, H2O, NaH3, etc. This is called as carbonyl. Nitrosyl, aqua, amine, AMM, not amine, ammonia, amine, AMMINE, amine, right? Now, negatively charged ligands. Negatively charged ligands. Example. In case of negatively charged ligands, E is replaced by O. Terminal E is replaced by terminal O. Right? F minus, fluoride, called as fluorido. Fluoride. You can call it as chloro also, chloro also, but preferred name is DO. NO2 minus, nitrite ion, nitrito. NO3 minus, nitrate, nitrato. SO4 2 minus, sulfate, sulfato. S minus 2, sulfide, sulfido. OH minus, hydroxide, hydroxido. Clear up, etc. And so on. So this is based upon charge. Next slide, sir. They have given, might have given so many lists, right? But this is the basic idea. Based upon charge. After that, based upon denticity. Second classification, based upon denticity of ligand. Classification of ligands based upon denticity of ligand. Break is up from. Time is there, no? Denticity means lone pair approach. If it is able to donate, one ligand is able to donate only one lone pair, then it is called monodentate. If it is able to donate two lone pairs, bidentate, right? So denticity of ligand means number of lone pair electrons donated by ligand is called denticity. Monodentate ligands. Monodentate dentate ligands. Means they will donate one lone pair of electrons. Example, sir. Cl minus, OH minus, F minus, N, ammonia. Nitrogen also donate only one lone pair, na? Amines or NH2, monodentate, right? Any other? Carbon monoxide. It will donate only one lone pair. Nitric oxide. Here also it will donate only one lone pair, right? Etc. Even though they have more lone pairs, they will donate only one lone pair. That's why they are called as monodentate, right? Yes, sir. In case of NO, either N will donate or O will donate, but anyhow they will donate only one lone pair. If any one of them can donate, then it is called ambidentate, right? Respond. But they are all monodentate ligands. This is ambidentate ligand. No, carbon monoxide is not ambidentate. CN is ambidentate. Cyanide, isocyanide. SCN is ambidentate, either sulfur or nitrogen, but carbon monoxide is monodentate. Only carbon is the donor. Even though oxygen is having lone pair, it will never donate. Reason? Consider carbon monoxide, carbon atomic number. After 2 years of chemistry, carbon atomic number is 4. Right? 6. Valency is 4. He's to some extent correct only. Valency 4. Outermost number of RB electrons are 4. So configuration 1s2, 2s. That's what. Nowadays we need to search what is correct in your answer. Accordingly, we will frame the questions. That is also good only. Till earlier at our times, for questions, we need to write right answer. Now, you write the answers. While correcting, I will write correct question for it. Accordingly, if I am able to find correct question, you will get marks. If I am not able to find question for it, marks will decrease. Correct or not? In such cases, we will write questions and answers also. 2s2, 2p2. Coming to oxygen, atomic number 8. Configuration 1s2, 2s2. How many unpaired electrons in oxygen? 2. So it can form 2 covalent bonds. How many unpaired electrons do carbon have? 2 and 1 lone pair. So it also can form 2 covalent bonds. So first I am forming 2 covalent bonds between carbon and oxygen. Oxygen have how many lone pairs? Hey. Now carbon have 1 lone pair and 1 empty orbital. 1 lone pair, 1 empty orbital. Into that empty orbital, this oxygen can donate lone pair. 1 coordinate covalent bond. If it donated lone pair, what about electron density on oxygen? Carbon. Now which is can act as a donor. So carbon monoxide, only carbon acts as a donor. It is not ambidentate. Clear? Don't go for excited state and so on. Don't do that here. Right? If I bring another oxygen, then go for excited state because it has to form more number of bonds and so on. Clear? You know MO theory also, right? If you take carbon monoxide, better let me write that also. At one place it is over. According to MO theory, configuration, sigma 1s, sigma star 1s, sigma 2s. How many electrons? Option 8, 14. 14 means pi or sigma, which comes first? So pi 2px equal to pi 2py, sigma 2pz, then sigma star 2s. This sigma star 2s energy rises. Now pi star 2px equal to pi star 2py, sigma star 2pz. Response, sir. Configuration totally 14 now. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, what is this? Unoccupied or occupied? High energy or lower energy? Among unoccupied. Among unoccupied. It is having high energy or low energy? Among unoccupied. These two are unoccupied orbital spans. Among those two, is it high or low? So it is called low unoccupied molecular orbital, LUMO. Correct? Now, among occupied, which is having high energy. Among occupied, sigma star is having high energy among occupied molecular orbitals. That's why it is called HOMO. High energy, occupied molecular orbit. Right? If carbon monoxide is donating electrons, from where it will donate electrons? Which electrons it will donate? Sigma star. That's why when carbon monoxide is donating electrons, it will form sigma bond. When it is accepting electrons, in which orbital it will accept electrons? That's why it is called pi acceptor ligand. Sponsor. When it is accepting electrons, it will accept electrons into pi star orbital. That's why it is called pi acceptor sigma donor. So it is an example of sigma donor pi acceptor ligand. Next see it. You have separate classification. Another classification is there. Classification of ligand after density based upon type of bond. Sigma bonded complexes, pi bonded complexes, sigma donor pi acceptor ligands, pi donor pi acceptor ligands. Under that, carbon monoxide comes under sigma donor pi acceptor ligand. Is it clear? Right? Bond order 3. Respond. Now, if I want to write CO plus, what is the name of CO plus? CO is carbonyl. CO plus is called carbonylium ligand. What man? Name ends with IUM. So CO plus carbonylium ion. What is bond order? From where I have to remove electron? Sigma star 2s. Correct or not? This is the higher energy. From here I have to remove electron. What is bond order formula? Number of bonding minus anti-bonding by 2. Bonding electrons 2, 4, 6, 8, 10. Minus anti-bonding 2, 4. 10 minus 4 by 2. 3. If I remove one electron, that's what. This is the only compound, only ligand having bond order greater than. We discussed this point. Correct? No element, no species is having bond order greater than 3. Only one species, CO plus. Right? In CO plus also, which acts as a donor? Carbon only acts as a donor. Clear? Any questions? What are ambidentate ligands? Either of the donor atoms can donate lone pair of electrons. For example, if you take NO, in NO, one bond is odd electron bond, correct? Sponsor, if oxygen acts as a donor, it is called, if oxygen acts as a donor, O nitrosyl. If nitrogen acts as a donor, same if you take NO2 minus nitrite, nitrito. If oxygen acts as a donor, then it is called, correct, O nitrito. If nitrogen acts as a donor, N nitrito. If a C triple bond N, nitrogen has lone pair, carbon has negative charge. If a carbon acts as a donor, cyanido. Over. Isocyanido. This one, cyanido. Same way, SCN. SCN. It may be, if I keep triple bond here, I can write like this also, no? If I keep triple bond here, I will write nitrogen with lone pair and sulfur with negative charge. If a nitrogen donor, sulfur donor, this one, thiocyanidO. In this case, isothiocyanidO, na? See the name in nomenclature of that table is there, na? IsothiocyanidO. Response, sir. The list is there, na? In that SCN. IsothiocyanidO. Oh, all these are ambidentate ligands. So we are discussing about classification of ligands based upon denticity, in which monodentate ligands is over. After break, we will see bidentate ligands. One problem came, sir, regarding D and A block. In D and A block, I thought of merging it. It got stuck. Right, complete knots gone. Right, so I am not in a position to upload it. I will try to retrieve it, or if I am not able to retrieve now, last year's notes I will post. Right. Go for break, sir.